Okay, let us start with today's external tech talk. Today we are going to listen to Professor Holger Caesar. Dr. Holger Caesar is an assistant professor in the Intelligent Vehicles group of TU Delft in the Netherlands. Holger's research interests are in the area of autonomous vehicle perception and prediction, with a particular focus on scalability of learning and annotation approaches. Previously, Holger was a principal research scientist at an autonomous vehicle company called Motional, formerly nuTonomy, and there he started 3 teams with 20+ members that focused on data annotation, autolabeling, and data mining. Holger received a PhD in computer vision from the University of Edinburgh in Scotland under Professor Dr. Vittorio Ferrari, and studied in Germany and Switzerland, PIT Karlsruhe, EPF Lausanne, ETH Zurich. He is best known for developing the influential autonomous driving datasets nuScenes and nuPlan, as known for developing, as well as his contributions to the real-time 3D object detection method PointPillars. In his spare time, he likes to hike with his small family, as well as sing, run across the Alps by mountain bike. So, we are waiting for your talk, Professor.
Okay, thank you very much for the introduction. And good afternoon to everyone. Here it's already rather late in the Netherlands. So yes, thank you for the introduction. I think everything about me was already said. So the title of my talk is Auto-Labeling Everything Everywhere. This title sounds a bit stupid, but it's inspired by the titles that I just saw at ICCV last week in Paris. The Best Paper Awards went to Tracking Everything Everywhere All at Once and Segment Anything. So it seems to be popular, these titles these days. What this title is about is auto-labeling the data that a company like Nuro collects. So really labeling all of the data that's collected, to index it, to use it, to learn from it, and labeling all of it, and especially also occlusion, data under occlusion. We will talk about that in a second. Yeah, this is my CV. I think most things were mentioned. So since last year, I have been with TU Delft as an assistant professor, working on all things autonomous driving. What people probably do not know very much is our group in general. The Intelligent Vehicles group is relatively big, 6 professors. We try to cover all aspects of autonomous driving, so machine perception, dynamics, control, planning, and even human factors such as motion sickness. So we are roughly 30 people, and we really try to cover all aspects. We have a nice kind of autonomous vehicle platform that we also use to collect data and also drive as a shuttle autonomously in the near future. And then we also have a simulator where we do a lot of user studies to see, especially in the context of motion sickness, but also virtual reality, augmented reality, things like that. Okay, now let's jump into the talk. So the background, the motivation for this talk is in the past, I have created a lot of data sets, and most of them, or in the beginning, those data sets were very manual. So you've heard about the nuScenes dataset, perhaps. This was in 2018. We annotated 40,000 keyframes, it's roughly 5 hours of data. Everything annotated by humans. We reviewed everything ourselves. So it was a lot of work, very detailed work. And of course, it's clear that these approaches don't really scale. If we do everything by hand, there is a limit to that. This data set, on the other hand, had some good advantages, some novelty. It was a first with radar, 360-degree camera coverage. We had nice HD maps with 13 different layers or something, like sidewalks, crosswalks, etc. We had good localization, so not just GPS, but we actually localized against the HD base maps. We have lots of rare classes, object attributes, such as our persons like sitting, standing, walking, etc. We have sequential data and also lots of diversity. So this data was collected in the US, but also in Singapore. So we have left-hand and right-hand driving, night, rain data, etc. So lots of diversity, which makes this interesting for studies. There's also another data set, which is a little bit smaller. This is the View of Delft data set created by the group where I am now in academia. And this is our prototype vehicle driving through the old town of Delft. Delft is a small town in the Netherlands. You have all kinds of canals. You have pedestrians, cyclists everywhere. Very few cars, actually. Very narrow roads. So this data set is really about these unique challenges. And also, again, the topic of occlusion. So occlusions are everywhere, especially because of the narrow road layout. So this is quite different from what you would expect in, for example, driving in Arizona in big cities. Okay, here's a table from the nuScenes dataset. This was back then a dataset comparison table. We can focus on the last, the third part of this table, which is kind of the modern 3D datasets. So we have nuScenes before, and then afterwards we had Argoverse, Lift, Waymo, A*3D, A2D2. And I think the most important aspect here is that there's only one dataset which is really the same size, and that's the Waymo dataset. It just looks much bigger because they sampled 5 times higher frequency. So instead of 40K, you get 200K, but it's really the same amount of data overall. These data sets are all like human labeled, but it is very interesting that essentially still 5 years later, 5 years later, we are still not having any bigger data set. And that begs the question, have we reached kind of the limits of what's feasible, or at least economically feasible, or why does nobody create anything that's bigger? Another related question is, are we making progress? So this is from the various challenges that we organized on the nuScenes dataset. This is the detection, object detection challenge. And you can see this PointPillars was a method that we proposed in 2018 that was state-of-the-art back then, but is now vastly outperformed. Then you see most of the winners of the follow-up challenges. So you get fusion methods, anchor-free methods, transformers, and really huge improvements overall. So that's great. One interesting observation is this narrowing LiDAR camera gap towards the end. Let me just remove this window here. Okay. So we see basically that camera is in red and LiDAR is in blue, and that they are relatively close these days. So that will make probably the Tesla fans happy. And another observation is that in the first 24 months that we organized this challenge, we had an improvement of 31% on this metric that we proposed, which is called NDS. And in the next 24 months, we only saw 3% of improvement. So that begs the question, is the performance saturating on this data set at least? Do we need perhaps bigger or more difficult data sets to really max out the potential of the methods that we're looking at? Okay, and this brings us to the nuPlan dataset and benchmark. So nuPlan is a benchmark for multi-agent simulation, or in other words, for planning of objects, of agents. And the background here is, this is a paper from Lyft that was released together with their dataset. And basically they were looking at this question, do we really need more data for machine learning based planning? And then they trained the same ML-based planner with different amounts of data. And you can see that with much more data, you have much lower number of interventions per 1,000 miles. And actually, if you look at the amount of data in nuScenes, that's only 5 hours of data. So there's a drastic improvement if you go from nuScenes amount of data to their amount of data, which is around 1,000 hours. But the interesting thing is also that the overall numbers here are still very bad. So 93 interventions per 1,000 miles is not something that you would consider safe. And this is only on a route of 6.8 miles with only 3 turns. So I think it's from their office to the train station or something like that. So it's clear that if we really want to scale, not just, the robotaxi application with a very simple route, but really to generalize to the whole country, level 5 of full autonomy, then we need much more data than this. So what we did is we looked a little bit at the landscape of data sets out there. There is a benchmark from TUM, the Technical University in Munich, which is called Common Road. And this is quite interesting. It's essentially a software framework for closed-loop simulation of scenarios, and you can use it for planning especially. The focus is not so much on machine learning-based planning, although they don't really, that's up to you in some sense, but the framework is not really made for that. And most importantly, it's a small number of handcrafted scenarios. Later, they also implemented some kind of tools to import other data sets, but the lack here really is their own data set. And there's also no sensor data, no scenario-specific metrics or no scenarios in general. So this is a planning benchmark, but it's only, it's lacking a large-scale data set behind it. Then we have 3 big data sets from Argo, Lyft, and Waymo that are increasingly bigger. They're all focused on prediction or motion forecasting, as some people say. The Argoverse dataset was really big at the time, 2019. It has maps, but rather low quality maps, and it has auto-labeled tracks. So the dataset is labeled, this really big dataset is labeled, but the quality is rather bad because it's labeled with the on-car perception system, which is, has to work in real time and is therefore limited. Similarly, the Lift dataset, I mentioned already, it's much bigger, more than 1,000 hours. It has good maps. It has, all kinds of different maps, even aerial maps, also traffic light statuses. But again, the perception tracks in the dataset are from online perception and therefore noisy. And finally, Waymo is a little bit smaller, but has 6 cities, so a lot of diversity. It has very high quality maps, and it also has a very high quality offline perception system that auto-labels the dataset, which is really crucial, as we will see later. But in total, basically, we have one benchmark for planning, but that doesn't have a dataset, and then we have 3 datasets that are not for planning. Okay, now comes nuPlan. So nuPlan is the world's first large-scale ML-based planning benchmark. It has around 1,300 hours of auto-labeled data from 4 cities, again in the US and in Singapore. It features a software framework with closed-loop simulation for evaluating your ML-based planner. And we also are the first to release sensor data on a really large scale. So this is 10% of the whole data set. And in comparison to nuScenes, this is probably 25 times bigger. So this is pretty big and very difficult to store this data on your hard drive. Here's a look at the topic of offline perception, auto-labeling with offline perception. So first, let's look at this video here. This is a teaser from nuPlan. Yeah, I think the quality is good enough. So we can see essentially the LiDAR bird's eye view in the middle, and then we can see all the camera views around. And really the quality of the boxes is relatively good. And we can also see how dense these scenes are. So we also made sure that the range of the perception system is relatively long to really include as many objects as possible with high quality. And the way we did this, let's just do this. The way we did this is somewhat inspired by both a Waymo and a Uber paper, which has 3 components. So first comes the offline detection, then comes a tracker, and then comes a track refinement component. This setup is interesting because the track refinement component is mainly the new part. So it kind of globally refines one track to make sure that it's smooth, it doesn't jump, things like that. And the advantages of using offline perception are that we can use a very resource-hungry perception method. So it can work in the cloud with many GPUs at the same time. That, of course, makes it stronger. We can use much deeper backbones, things like that. But also that it is acausal. So that means we can look at the past data, but also at the future, because we're doing this whole thing offline. Yes, so many advantages, especially the quality is much better. We can essentially think of the tracking problem as finding a global solution for a scene, let's say of 20 seconds length. And Waymo showed that this kind of approach can actually achieve human level labeling performance for cars at a low IOU threshold. There's not human level labeling for all classes at all IOU thresholds, but at least if you only look at that, it is really good already. And then, of course, the bicycles and things like this will be harder to annotate. Okay, here's the planning framework. So the idea is you train an ML-based planner, you simulate the planner, but also the other agents in the scene. You measure the performance in a number of different scenarios, and then you can compare and visualize different planners and look at number of metrics, but also visually how are they doing against each other. And then we have 3 different challenge formats here. Essentially, we have log replay, which just means everything is in open loops. So you're literally just playing back the log and ask, what would you have done? But you're not actually simulating the interaction between ego and agents. Then we have simulation of only the ego and the agents, which we call reactive agents, where everything is in closed loop and we really play through what would happen if you implement these actions. We have a modular simulation engine. So we have here, especially on the left side, the observations, which could be either raw sensor data, images, point clouds, or it could be boxes. Then we have the planners that could be learned methods or rule-based methods. Similarly, the agents can be learned or rule-based or just playing back what happened in the real world. Then we have the controller, can be perfect control or a more kinematic, more realistic controller. We have open loop and closed loop simulation. We have different metrics that we can plug in, also specifically for the scenarios. And then we have a nice dashboard to visualize everything. The idea is really that you can go and implement one new agent model and just test out how it works without having to re-implement everything. What we also did, and I already mentioned this, is we extracted a number of different scenarios, I think in total 71 different scenarios. So essentially, we handcrafted rules for what is an unprotected cross-turn, what is a jaywalker in front of the vehicle. Then we kind of wrote certain queries in SQL and ran that on the whole data set, which took a long time. And then we get these tags out of it. Then we curate them manually to make sure that at least they have a very high precision, maybe not recall, so we're certainly missing some, but the ones that we return are relatively high quality, so I think over 90% precision, and therefore you can be very confident that if you're evaluating your planner on these scenarios, you know how well your planner is doing on those scenarios. Another thing that we did is to look at the traffic lights. I mentioned already that Lyft and Waymo had traffic lights, but they just used an on-car perception system. So it's essentially, let's say, 2D object detection of traffic lights and then figuring out the status in there and associating that with the map. What we did instead was a different approach. So we look at the motion of the agents in the scene. And if they're not moving, then, if they're moving across the intersection, that means it must be green. And if they're stopping at just before the intersection, then it means it must be red. And if there's no observation at all, then we are conservative, and then we essentially also set it to red, such that the scenario, if we played back in simulation, would be as similar as possible to the real-world scenario. So that has, of course, the advantage that we're not just covering the directions that we're actually observing, but really that we're covering all possible directions and therefore getting more data. And we just quantified that for our latest archive submission. I think it's 5.3 times more traffic lights that we get statuses for than with the perception solution. Okay, then we organized a number of planning challenges on this benchmark. And here are some of the results. So we have a number of baselines. We have a simple planner that just keeps on going straight. We have the famous IDM planner, although with some improvements, that essentially follows on rails, so basically follows the lanes unless it's running into an object, then it will slow down before that. And then we have a more state-of-the-art machine learning-based method that also is learned and takes into account the map. That's called the urban driver. And if we look at the open loop results, we see that the ML-based planning method, the urban driver, performs much, much better than the rule-based baselines that we have here. So that's what you would probably expect, since given that the urban driver is much more complicated. But if we look at the closed loop results, it's quite interesting that suddenly the IDM planner and the urban driver are almost the same, or in fact, the IDM planner is even better than the urban driver. So this seems to show that in closed loop, a method trained on open loop does not generalize very well. So there's this domain gap between open loop and closed loop, and therefore it's not performing well in kind of new scenarios. Another observation was from the challenge participants. There is a new state-of-the-art method called predictive driver model, PDM. And this method is interesting in the sense that it combines two approaches. So for short-term planning, it uses a rule-based method, and for long-term planning, it uses a learning-based method, and kind of combines them, and therefore they are state-of-the-art both on open loop and also on closed loop. Okay, another question is, do we really need offline perception, or can't we just use online perception as Lyft and Argoverse did? And we ran a simple experiment where we used the offline perception that we have in nuPlan, but then we also lowered the quality to be at the level of the online perception, and we ran an ML-based planner on both of them and measured the planning score according to nuPlan. And we see that offline perception gives us a 7% higher planner score. So that's promising. That really shows that perception quality matters. And then many people would probably do some kind of data augmentation to the planner. So then is the question, if you're doing data augmentation, adding noise to the data, does it then still matter? And we were able to show that even with a reasonable amount of data augmentation, you still get a 5% improvement on offline. So it really seems to matter what the original perception quality is like. So let's conclude this first part. nuPlan is the world's largest labeled autonomous vehicle dataset, which is labeled with auto labeling, so it's no longer human labeled, luckily. Earlier datasets focused on perception, like nuScenes, and prediction, like the other three datasets that I presented. But we aim to push machine learning-based planning with this dataset. We have a relatively unique dataset due to the raw sensor data, the scenarios, the traffic lights, and also the closed-loop evaluation. It's a nicely modular framework that allows you to test new planners, agents, and controllers. And there's a new state-of-the-art, which uses a hybrid planning technique that combines the strengths of both rule-based and learning-based methods. Okay, so now let's do a little check-in here. Where are we in terms of auto-labeling? So what did we do for nuPlan? The detection was auto-labeled with offline perception. That sounds good. The tracking was auto-labeled, but actually using a standard online perception method. And that was the same for the Waymo and the Uber method. So that's one thing we could improve. The traffic lights are offline labeled with auto perception, auto labeled with offline perception. So that's good. But the scenario classification, as I briefly mentioned, is still kind of semi-automatic and then just some human QA afterwards. So that can also be improved. So let's try to fix these two aspects in the rest of this talk. So this paper is called Graph Convolutional Networks for Complex Traffic Scenario Classification. And the motivation for this work was that it is probably not feasible to collect enough data to make a safety case by just randomly driving. Some estimates say, this is the often cited number, that you need 275 million failure-free miles of driving to kind of prove that your car is safe. And then if you have an accident, you essentially need to start again. So this is not really feasible. So the most promising approach to address this seems to be to focus on safety critical scenarios, and thereby, because we know that they are safety critical, drastically reduce the number or the amount of driving data that is needed to make this safety case. And there is already EU regulation that tries to address this, or I think it's a draft at the moment. They essentially recognize this and they define a set of key scenarios. So it's a not very long list of scenarios that all these car makers should test for, and also autonomous vehicle providers. So what we did is we worked with this list. It's a little bit longer than what you see on the right side. It's maybe 15 scenarios or so. We removed some scenarios that didn't work for us, such as crashes, because we don't have crash data, at least not in public data sets. But we worked with all the scenarios that are relatively frequent enough, and created a curated list of them. And then we annotated nuScenes and also a part of Argoverse, so in total 20,000 keyframes, manually with the scenario type that you find there. The assumption is that every frame has only one scenario for the ego vehicle. Yeah, we can look at an example from this data set here. I think this is from Argoverse. So you see 0 is no scenario. That means we're just essentially going straight. And now it's a little break. And now we will start a left turn. And the ground truth says it's an ego lane change to the left. And then again, we are in the lane. And then we have no scenario. And you see already that it's kind of really difficult to time exactly when should be the start and end of a scenario. That's a problem we had a lot, both when doing it manually, but also when automating it. Okay, let's move on. Then we presented a method, which, as I said, is based on graph convolutions. So we construct a graph, which is essentially all of the nodes of the ego vehicle, but also the other vehicles, and then also kind of regularly sampled points on the lane center line. Then we also have the adjacency, which essentially just says if a car is within a certain range of the ego vehicle, then it's it's adjacent. And then we have several components. First part is spatial aggregation block. So this aggregates, first of all, the environment, but then also the agents. Then we have a temporal aggregation block, which is very simple, just a temporal convolution over the temporal dimension. And then we have a simple classification head, which outputs these 8 scenario types. And the yellow blocks here are graph convolutions. So in the spatial aggregation, that's mostly based on graph convolutions. There are a number of scenarios and a number of challenges with this problem, with this application here. One is the exact scenario timing. Already mentioned, it's very difficult to exactly time that. So what we have is, first of all, accurately labeled, frame level labeled data set, which didn't really exist before. And then the other aspect is we address that with temporal convolution. Then we have egocentric scenarios. We address this egocentric aspect by centering the coordinate frame on the ego vehicle, which other methods didn't do. We have class imbalance, very extreme. So most of the scenarios are just going straight, nothing happens. So we mostly address that by cropping the data set around the meaningful scenarios and just leaving a kind of random margin before and after. And then we have the challenge of how do you encode the relations between the agents and the environment. And as shown, we use graph convolutions to encode that. Here are some results. So we see the different types of scenarios again, then our result, and then the most important method that exists at the moment, Müller-Varapo et al. And we can see that our accuracy is much higher on the ego scenarios. So that's at the bottom, 62.3%. Whereas on the all scenarios, including the agent scenarios, we perform only slightly better than the existing method. So the strength of our method is really in performing very well on ego scenarios. And the focus is not so much on kind of agent scenarios, such as cutting in or stationary vehicles in the lane. Okay, here's another example of our method. So to recap, 0 means no scenario. 1 is a lane change. No, is a vehicle cutting in, and 2 is a stationary vehicle in the lane. And if we watch this again, you will see that in the beginning we had no scenario. Then these two have some confusion here. So in the beginning, this car, when it's cutting in, the velocity is very slow. So it's a bit hard to figure out, is this stationary or is it moving? But then as it starts to really move, the class number 1 will dominate. And then it's clear that this is was an ego vehicle cutting in. And when it proceeds, then that goes back to just the 0 scenario. Okay. So now we kind of addressed the scenario classification part, although to be fair, it's still a very limited number of scenarios. So this was only 8 classes. If we want to extend this to 100 different scenario classes, then it will be much harder for sure. Now let's focus on the tracking part. There's a work called Offline Tracking with Object Permanence, was just released on Archive. And the motivation here is that in multi-object tracking, occlusion is a very big problem. So many detectors, of course, miss occluded objects, even semi-occluded objects, or the trackers miss it because there's no notion of object permanence. So typically how trackers work is they track an object, and if it's not seen anymore, they will keep it for a number of frames around, and then at some point they will drop it if they haven't seen it. So that is definitely a problem. And then when you see the object again, you will essentially think it's a new track. So you have an identity switch. And that's very challenging, especially for auto-labeling, if we want to really create very high quality tracks here. There's one example at the bottom. We have a car, then we have a truck passing by. So the car is, I think it's still a little bit visible at the bottom, but it's mostly occluded. And then afterwards we see it again, and then the tracker would give it a new ID, which is called identity switch. Existing offline auto-labeling methods, as I already mentioned, are especially the paper of Waymo and of Uber, and they focus very much on the bounding box quality, but they don't focus on the tracking part. So the tracking method they use is the famous AB3D-MOT, which is a very simple Kalman filter-based method with constant velocity assumption. They don't improve the tracking part. They're just interested in improving average position. Our method, in contrast, tries to also have good boxes, but then also focus on the tracking part. We focus on 2 steps. We have 2 steps. The first one is accurate association, and especially in those occlusion cases. And the second one is recovering from those occlusions. So really filling in the gap, what happened while we did not see the car. Because for auto-labeling, that might still be very interesting. And then in contrast to the previous methods, we look at tracking metrics as well. Here's an overview of our method. So our method just starts with a standard online tracker, the same one as the previous works used. And then it has 2 more steps. First one is re-identification. So essentially, I have my past before the occlusion, and I have a future after the occlusion, and I want to match these. and figure out which future is the most likely future. And then I have, as I mentioned, the track completion part. So that just kind of fills in the gap in between the past and the most likely future and gives us a complete track. This is our re-ID part, re-ID method, and it's the map branch. So this learns to encode the map and also the agents. This is also a little bit similar to what we saw in the previous paper, and it's inspired both by lane GCN and then also general global attention mechanisms. So again, you're kind of trying to represent both the map and the agent, and then have kind of attention mechanisms between agent and lane, then global attention, then back from the lane to the agents, and then compute some affinity score. Another part is also a motion branch. So we don't just look at the map, we also look at the motion, and we essentially say between the past and the future, just compute a score from the trajectory without looking at the map, how well the past and the future are kind of agree with each other. And this, of course, has the advantage that it can learn nonlinear motion as well, which many existing methods do not. And then the track completion component looks also a little bit similar. It's interesting to note that this track completion is really very much inspired by motion prediction or motion forecasting. But one big difference is that in motion forecasting, you only have the past and not the future. So here we have the past and the future. So in some sense, it makes it much easier, but we can reuse a lot of those methods. And another challenge is that for the motion forecasting task, typically you have a fixed time horizon. So you say, where will this car be in 1, 2, 3, 4, 5 seconds? Here we have a variable time horizon because occlusion is not fixed to a certain length. Occlusion can have any kind of length. So we need a mechanism to encode these time queries, which is shown here at the top right. So essentially, we literally encode the time as a query into our network, and that makes it very flexible. We can ask at any point in time, at any level of resolution in terms of the floating point number, where was the agent at this time? And then again, we have the motion encoder, lane encoder, and the previous components here. So what are some of the challenges with this project? We have online trackers can have many identity switches. We use prediction for re-identification to overcome these identity switches. Then missing occluded, we often miss occluded object trajectories. Our solution is to repurpose prediction as track completion. So when we have occlusion, we can essentially fill in the gaps. Another challenge is there's no ground truth under occlusion. This was actually a huge problem. Like we're filling in the gaps, but how do we know that we're doing well? And our solution to this was mostly to insert pseudo inclusions into data that does not actually have occlusions. Of course, not in the test set, but at least in the training data, you can do this as a form of data augmentation. And then you know very well how the car was moving, and you can just simulate occlusion essentially. Then we have the variable occlusion duration. This was addressed by encoding time as queries. And the other topic was occluded motion is not always linear. So often it follows the lane, which can be turning, for example. We address this both with the map and the motion branches. Here's some results from the re-ID part. So if you take a very simple constant velocity model as a baseline, then we only associate the past and the future accurately in 60% of the cases. And if we have our motion and map branches, it goes to around 90%. So that's obviously much better. And this is often you have, let's say, around 30, 40 vehicles in the scene. So this is basically 90% accuracy when matching it to one of those 30 or 40 vehicles, which sounds relatively good. And then if we inject this re-ID component into our tracker, we get a result of here at the bottom. So this is the AMOTA, the kind of main tracking score in nuScenes of 72.9. So this is slightly better than the state-of-the-art Immortal tracker. It's especially better on the car class, so slightly better on some longer classes, which we think could probably be tuned a little bit better. But overall, it's very encouraging to see that we do have state-of-the-art results. And in addition, we are also filling in the gaps, right? So we have this track completion component. And we actually tried some different methods here as well. So you can see the average displacement error inspired by the prediction task. And for a baseline based on the famous home method, we would get an error of 80 centimeters. For our motion branch, we get 70 centimeters. And if we also use the map, we get 66 centimeters, 67 centimeters. So this is really relatively accurate using our track completion method. Okay, here are some qualitative examples. So when this little arrow in the box is red, that means it's from the online tracker. And when it's blue, that means it's the filled in gaps in between. And we can see that this looks very reasonable, very smooth. Yeah, and it's also turning nicely, as you would expect. Okay. Before I conclude, just one more project I would like to mention, because this also deals with occlusion. So this is a little data set that we created in simulation in Kala, to be precise. And this is essentially, the idea is you have a drone flying overhead in a city. In this case, the drone is actually following exactly the vehicle, the autonomous vehicle on the ground, but this will also be changed in the future. And the question is really, what if we had drones flying in the sky? Would that make autonomous vehicles safer if they follow us? Because the idea is, of course, that if you have a building, the vehicle cannot see through the building, but perhaps the drone can see on the other side of the building and therefore see more. Or if you have occlusion by other objects, then you can likewise see more. And yeah, this is still ongoing work. So it's called the Horus dataset. We already have the dataset, but we're still kind of doing some extensions there. And initial results show that if you do essentially fusion from the drone and the camera on the Ego autonomous vehicle, then you get significant improvements, 5% overall, and much more improvements on classes like bicycles. So that's kind of exciting to see that this idea would really help. And we're also extending that now to the planning task to really see how many fewer accidents would you have if you, assuming hypothetically you had such a flying drone in the sky. Okay. In conclusion, so to train autonomous vehicles end-to-end, we need much more data than we currently have. Manual labeling does not scale very well. We really need auto labeling. We introduced two improvements here. One is traffic scenarios are still entirely labeled manually. So we attempted to auto label them, at least a small number of them, 8 in this case, which worked relatively well. And the second improvement is while auto labeling nearly matches the human performance, it still struggles, especially with occlusion cases. So we have a tracker, offline tracker that focuses on occlusion cases and can reconstruct them, and also has state-of-the-art results in terms of offline tracking. And we also showed that in nuPlan, if you use an offline versus an online tracker, you really get much better performance if you train your planner on the offline perception. Okay, and the ongoing work was the question, can occlusions be reduced by controlling a drone to fly ahead? And preliminary results seem to show that, yes, it can. Okay, thank you very much for your attention. And if you have any questions, feel free to ask.
Thank you, Professor Holger. First of all, let us thank our speaker today. And I hope all the audience joins us. I think we have already the question from Yanis. Yanis in the Q&A session. Yanis, you probably can ask it directly.
I wouldn't call it a question. It's more like a request to share the relevant papers after the talk. But yeah, great talk. Thank you very much for sharing everything today.
Thank you. I think we will probably share the slides, perhaps. Then you would find the references in there.
Yeah, I was going to suggest it. So if it's okay from Professor Holger's side of view, then yeah, I will share it probably the nearest time.
Okay, sounds good.
Yeah, thank you so much for the talk. So yeah, I think you mentioned that auto labeling is very important for many of the tasks. But I think the other trend is like end-to-end kind of a driving, right? Which is like UniAD, for example, like the occlusion thing that you mentioned. Maybe those occlusion is encoded in the query interface, or like maybe so or like some of the self-supervised learning, right? Like where you probably don't need this auto label at all. What's your viewpoint of these two different approaches?
Yeah, it's a very interesting topic. I'm interested in all of those topics. So self-supervised learning, where I have two of my team members working on, I think it's a little bit, it's more of an academic topic. I think, it's nice that self-supervised learning gets you into, like, it generalizes relatively well, but I think of it more as a kind of pre-training stage. And as a company, I mean, it doesn't make sense not to, let's say, label any data and just, you will always have data, and then you might as well label a little bit more as a company. So I think self-supervised learning is mostly a good initialization, but I don't think it really solves everything. I think it just is like like pre-training a network essentially. End-to-end models are a very interesting topic. There are, of course, we saw very impressive results from WAVE last week. There was this Gaia one presented at ICCV. So these kind of world models, everything trained end to end, very nice. But I do think, especially for an autonomous driving company, I think it's still very far away from these systems being usable. First of all, I think they're not there yet, but really the main problem is probably the explainability, interpretability, that you cannot certify these systems. So I think academically speaking, they're very interesting, but I think in the real world, they will create a lot of problems because it's just one deep neural network, let's say. So you have no control over what happens there. So in that sense, I think, yeah, in the real world, they don't have that much impact yet, even though in academia, they're really changing a lot of things at the moment.
I see. But I think like the end-to-end thing, I mean, they still have like some intermediate outputs, right? Like you still predict track. And I mean, like say for example, if, maybe like perception detector, you are using like ML model, you cannot understand. And then maybe tracking, you can also use ML model, right? Which you can also not understand, but you have some outputs. That's like the thing that a human can understand. And then like a behavior model is like getting this track. And then, it's another ML model, you don't understand what the decision mechanism. So, if you have a system instead, which is not just producing these intermediate detection outputs, and you do tracking, and then you plug into behavior model, but you have like this query interface, you still decode from the query interface, so you at least you understand, what the model says, and then, but instead of passing directly the explicit bounding box, you pass in the query embedding, so to the behavior model. So from ML perspective, it seems like it's the same as before. Like there's a lot of non-interpretability, but also like your system also output these intermediate outputs for human to, at least have some understanding. So yeah, I
Yeah,
don't know.
it is interesting. Also, I think there are many different systems that call themselves end-to-end. So some of them have auxiliary losses, for example, for object detection, right? Some of these companies actually still label objects. So it's not like it's completely gone and it's just, you just have sensor data going in and trajectories coming out. So many of them have intermediate stages. I do think, though, it's interesting to kind of backpropagate through the entire stack, right? So that's the typical problem when you have modular teams, perception, prediction planning, that the communication between them is very difficult. So, having this gradient backpropagated through the different teams and therefore parts of the pipeline, I think is an interesting idea, but it also makes it much harder for a company to know what's really happening, right? So I think a lot of companies like this traditional way of working where you say perception works, now we move on to the next component and try to fix that, rather than kind of tuning everything jointly, which can be a bit confusing.
Okay, cool. Thanks.
Dear colleagues on the line, any other questions? Oh, probably I have like a little bit off-topic question, but how was the ICCV? Could you please share your impressions? Do you have any game changer, or it's like everything like gradually improving and improving?
Okay, so the question was, were there any game changes at ICCV?
Mm-hmm. Yeah.
Yes. I mean, perhaps we can do this, without recording. I think the wave contributions, Gaia 1, Lingo 1, they were really impressive. At least they drew in the biggest crowd. So the world model that can really project forward what's going to happen in the future, that's really impressive. Also, the way they essentially generated a scene then, so actual images of London, driving in London, just making up things, all kinds of possible future scenarios. So, what happens if you run into this building? What happens if you go straight? And all of them look relatively plausible. That was very impressive. And then the other part was the language model. So they really managed to, I don't know if you saw that, but they managed to essentially make the autonomous vehicle interpretable by just explaining its actions. So it would say, if there's a jaywalker, therefore I'm slowing down. So I think there's still a lot of room for improvement, but I think these systems are interesting, not just for autonomous driving, but also elsewhere. So that was one release. Apart from that, a lot of nerfs. So I was impressed how many problems you can solve these days with nerfs. I thought in the beginning it was more like rendering, but people are doing SLAM, localization, mapping, all kinds of different topics with nerf. So that was quite surprising to me.
I see. Yeah. Thanks a lot. Yeah, I think like the trend has begun even on CPR this year. A lot of nerf and a lot of incorporation of like language models, but probably not into the driving area at that time. Right now, it's already in the driving area.
Yes.
If no any other questions, let us thank our speaker one more time. It was a nice presentation. Yeah, I really appreciate it.
Thank you. Hopefully next time I can make it in person.
For sure, we are waiting for you. Definitely. Okay. See you.